Okay, in this lesson, we are going to look at how we classify different types of matter, and specifically, we're going to look at mixtures. So let's start by looking at this graph here. Matter, all substances on Earth can be classified as matter. Anything that has mass and takes up space, it's all matter. But we can break matter down further into different categories. Over here, we have pure substances, which we'll talk about later. And then over here, we have mixtures. We're going to focus on mixtures today. Mixtures are exactly what they sound like. There are multiple things mixed together, but they're not actually chemically bonded together. They're just mixed. And I'll give you some examples in a little bit. Mixtures can be broken down even further into what we call homogeneous mixtures or heterogeneous mixtures. And we'll get into the differences between those here. So let's start with a homogeneous mixture. The prefix homo means the same. So if we have something that is a homogeneous mixture, it is a mixture that has a uniform composition throughout. Okay, uniform composition throughout. Uniform means it's the same. So when a basketball team wears a uniform, they all look the same. Okay, they're all dressed the same. In a homogeneous mixture, the entire mixture looks the same. It's the same throughout. It's oftentimes referred to as a solution. So if you hear someone say a saltwater solution, it's salt and water mixed together uniformly. So it looks the same throughout. And if you've ever looked at a saltwater solution or a saline solution, you can't differentiate the salt from the water. It's just evenly mixed together. So here's some examples. I already mentioned salt water. Salt water is a homogeneous mixture. When salt is mixed with water, it completely dissolves, and you can't look at a glass of salt water and pick out the salt separate from the water molecules. It's all just uniform. Another example is vinegar. Vinegar is actually a mixture of water, excuse me, of water with an acid, a weak acid that gives it that flavor, but you can't look at it and see the acid separate from the water. Kool-Aid is another example. If it's made properly and it's mixed thoroughly and there's no sugar sitting on the bottom of the pitcher, if it's completely mixed and uniform, Kool-Aid is a solution. It's a sugar water solution, because Kool-Aid really is just flavored sugar. So those are homogeneous mixtures. If you look at those, you can't necessarily tell that there's multiple things in there. It all looks exactly the same. Heterogeneous mixtures, on the other hand, are mixtures that do not have uniform composition throughout. And so you could easily pick out which ones are you could pick out certain parts. So while we mentioned a team is uniform because they're all in the same, they're wearing the same thing. If you look on a basketball court during a game, that would be an example of a heterogeneous mixture because half of the people on the court are wearing something different. Okay. And it's easy to pick out which team is which because they're very obvious in the differences. So the different parts of a heterogeneous mixture are often visible. Not always, because we're talking in chemistry sometimes about really, really small particles, but they are often very visible. So here's some examples. Trail mix. The different components or parts of trail mix are very easy to differentiate, to pick out. You can very easily see them. So when my kids were little, they would go into the trail mix and they would just pick out the M&Ms and eat the M&Ms. And they could do that because the M&Ms are very visible and they're easy to distinguish from the other parts of the trail mix. Sand. Here's an example of something where the particles are significantly smaller and yet you can still see differences. If you've ever looked closely at a handful of sand, some parts are larger than others, some are darker than others. Okay, so there's obvious visible differences within that mixture. Pizza is another example. If there's something on a pizza that you don't like, a lot of times you can just pick it off, and you can do that because it's very visible and you can see it. Okay, so that's the difference between homogeneous mixtures and heterogeneous mixtures. Now, sometimes it's not always easy to distinguish the different parts in a heterogeneous mixture because they are maybe the same color or very similar in size or really, really small. But there are oftentimes other clues that help give it away. For example, raw milk. If you've ever had milk that came right from a cow, it is a heterogeneous mixture. And you can't necessarily tell just by looking at it, but if you let it sit in the refrigerator overnight, the cream from the milk will rise to the top and settle on the top, and you can see a layer of cream with the milk underneath it. Okay, and so that's the heterogeneous part. Now, if your milk is homogenized, then they go in and they make the fat particles a little bit smaller so that they don't separate out. But let's talk about separating mixtures because we can use the different properties of a substance in order to be able to separate those mixtures. A lot of times the things mixed will have different properties that you can use to separate them. For example, if I were to mix iron filings, like fine iron filings with sand, okay, all those particles are really, really small. And if I wanted to separate them, I might be able to sit and pick with my fingers or with a pair of tweezers and separate them, but it would be really, really time consuming. But if I focus on the properties of iron, iron is magnetic. And so I could simply run a magnet over that mixture. The particles that are magnetic will come up and stick to the magnet, and the stuff that isn't, the sand, would stay behind. So you can use properties of a mixture to be able to sort of separate them like that. A couple of ways in which we separate mixtures are given here. One is filtration. Filtration is used to separate a mixture based on particle size. So if you've ever looked closely at how we make coffee, okay, there is water poured in with the coffee grounds, but then the coffee filter, will separate out the grounds from the liquid because the water or the liquid coffee, can pass through the filter and the coffee grounds cannot. Another example of this would be if you're making pasta. You cook the pasta and then you want to strain it. Okay, you filter out the water, that you filter the pasta in the water by simply pouring it into a strainer or a colander. The water will fall through and the pasta won't. It's got holes that are small enough to stop the pasta. Now, you couldn't use a strainer or a colander to make coffee because the holes are too big. So you have to be really careful when you choose how you're going to filter something based on the size of the particles that you want to filter out. Distillation is another way that we can separate mixtures, but distillation is a little bit different. It's used to separate a homogeneous mixture, okay, using the different boiling points. So if you've ever watched the show Moonshiners, they set up a distill. And a distill is a way to separate the ethanol, the alcohol, from water. Inside their solution that they've made, they have ethanol and they have water. And what they want to do is they want to get just the ethanol. So what they'll do is they will put the mixture into a flask like this, and they'll start heating it up. But they'll heat it at a temperature which is low enough that the water won't evaporate. Only the alcohol will evaporate. So that the alcohol will turn from a liquid to a gas and it will evaporate into this tube. But the temperature is not warm enough for the water to evaporate, so the water stays behind. And when the ethanol gets into this tube, it'll condense, it'll turn from a gas back into a liquid, and then it'll drip into the separate container in which we are going to catch it. So that's how distillation works. It separates a solution using different boiling points. Distilled water is the same thing. Regular tap water has all kinds of minerals in it, and if you want just pure water, you'd have to distill it. So you'd pick a temperature in which the water would boil, but the things that are dissolved in the water will not. And so then the water would evaporate, turn into a gas, and then once it gets into the cooling tube, it will condense again. And that's how distillation works.